to be opposes the here the electric field, applied electric field. Okay. So here in this electrical conductivity, we can go for the drift velocity, resistance, resistivity, and electrical conductivity, Ohm's law, and also temperature coefficient of resistance. So here itself it is given out in this paragraph. Uh, Whenever a conductor which is going to be offering more charges, so that which may have a more and more plenty of free charges which are to be available, so that when you apply an external electric field to it, then the charge carriers which are going to be moving uh, uh, through the conductor, so that these charge carriers, so that these free charges in a metallic conductor, which you can call it as electrons, free electrons. So these free charges which are uh, moving as a ions and both positive and negative. So a gas under proper conduction, that is nothing but here a neon gas in a neon bulb. So which is also a conductor, but the free charges which are positive ions and negative ions and also electrons. Okay. The motion of these free charges which is going to be constituted a current here. Okay, I equals to Q by T. The ratio of the magnitude of the charge to the rate of change of charge, which is nothing but here a current. So that's what here the motion of the free charges, which is going to be constituted a current here. And also you need to find out that here the current, a current in a conductor, which is also maintain the electric field as well as the potential gradient, which is a constant here. So even though magnitude of the electric field which is going to be fluctuates, if we are going to be maintaining the electric field direction as the same resulting current, which is called it as a direct. If the field is going to be reversed, the direction periodically the charge flow which is also reverse. So the current which is a alternating current. So here a direct and alternating currents, DC as well as the AC. The thing is that here you can imagine how the free electrons which are to be moving in a current carrying conductor. So you can imagine that here this is the conductor. Okay. So the area of the cross section of the conductor is capital A, and these are the negative electrons. Okay. These are negative electrons which are moving towards in this direction. So plus minus. Electric field is there, battery. So in this direction, the electric field, if you apply, the motion of the electron which is going to be opposes the electric field. Okay. What is the velocity which is possessed by the free charge carriers? V. Okay. But the thing is that if it is going to be opposing means here, it is going to be colliding with the ions which are present inside the conductor, and also it is going to be collides with the walls of the conductor, and it has to maintain such a average velocity after getting this. So this is the case, average velocity. These are to be the motion of these electrons which are subjected to the thermal energy and the result in a random motion of the electrons. Okay. So V into dt is nothing but a distance. Distance formula, speed into time. So the speed of the charge carriers is V and the time is dt. So how much of the distance these free charge carriers, free electrons, which are moved inside the conductor, that is going to be representing from here to there. This one. Okay. So the thermal motion, which is a random one, and also for out present purpose, it may be ignored. Is it okay now? Yeah. So in this itself, it may gives you here if the E the charge on the electron, that what is the total charge which is crossing the unit area within a, within a time dt, which is given by dq equals to n. N is the capital N number of electrons are there. A is the area of cross section. E is the charge of the electron. Vd is the drift velocity of electron. Dt is within the time. Okay. What is dq by dt? If you say that I in this equation, from this equation, if left side comes dt here, dq by dt, which is nothing but a current. So what is the remaining? I equals to NAEVD. Getting my point? This one. If dq by dt is there, that is I. I equals to this. V suffix d, not V into d. Okay. So if you want to calculate the current value, you can easily get it with respect to the drift velocity. But what is the current density value? Current density is nothing but a J. J is IA. So it depends on the ratio of the current to the cross sectional area. Okay. J equals to I by A. Here a print mistake. I by A. Okay. This one. Current density. By substituting A and get cancelled, remaining is this. Current density. So this may be representing a current value. How current I equals to surface integral J. I equals to J. Next is the drift velocity. So we think of the charge carriers, electrons in a metallic conductors as a small particles of the charge. So the charge carries random thermal motion. Okay. So in a metal, the electrons which are moving even in the absence of the external electric field capital E. So if an electric field is going to be applied, the motion of the electrons is slightly modulated by the force exerted on them by the field. So while undergoing a rapid random motion due to the thermal energy, it is going to be slowly drift in a particular direction under the action of the thermal electric field. So you can see here how the electrons which are moving randomly, okay, there is in no particular direction of the electrons. This one. Random motion of the electron. You can easily know here. So that it is going to be given out here. An impressed electric field causes the electrons to drift with a velocity Vd toward the right. So what is the direction of the opposites? Tell me. If drift velocity which is in E in this direction, capital E should be in this direction. Okay, what is the direction of the E means opposite. That's what this diagram indicates. You can see area of cross section is capital A. This is a conductor. What is the length of the conductor? Small l. Applied the electric field in this direction, the motion of the charge carries electrons in this direction. Getting my point? What is the drift velocity? Drift velocity in this direction. Why? Because of here electrons which are moving. Electric field opposing. Is it okay? So the formula should be like this. Not one I by I. J dot A is I, not one, which is I. I equals to J by I. J కదండి. Next is the resistance. What do you say resistance? In a conductors, charge carriers which are not perfectly free to move. Okay. So conductor means it is going to be offering the charge carriers move freely. But the thing is that in particular cases, the charge carriers which cannot be allowed freely here. That means something which is going to be opposing. Okay. So in this here, the charge carriers which are not perfectly move. So in which direction the charge carriers are going to be moving here? What are the charge carriers which are present inside the conducting material? Electrons are the charge carriers. So that by applying such a potential difference between the ends of the conductor here, the charge carriers which are to be moving from one to another end. So the thing is that here how these are going to be moving, in which direction, in which way it is going to be moving here. So that the path of the charge carriers which are in a zigzag path. Just now we already discussed it here. This is the zigzag path. Okay. So you can easily estimate that here the zigzag path, the charge carriers are going to be moving here. So that in this way here there is a collision is going to be taken place between the charge carriers and also with the walls of the conductor. Here friction is going to be developed. When the friction developed, temperature rises. Okay. If temperature rises, then something which is going to be opposing the charge carriers to move from the one to another place across the conducting material. That is the case. That means something which is going to be opposing. That opposing term you can call it as a resistance. Is it clear? So in this manner, you have to know about the Ohm's law. Ohm's law, which is going to be denotes that here, whenever such a potential difference which is going to be applying between the ends of the any conducting material, then which is always proportional to the here current which is generated in the same material. That means V is proportional to I. Okay. Or else V equals to IR, where R is the proportionality constant. Where R equals to V by I. This is not VLI. So many print mistakes are there. You can go for the R equals to V by Right. So this is the Ohm's law. V which is measured in volts and IA which is in ampere. Volts per ampere is nothing but a ohm. So which was said by the ohm here on his name only we are to be giving out the units for the resistor is a nothing but a ohm. Okay. So this is only the definition. The thing is that here you can go for this Ohm's law. So this Ohm's law V equals to IR which is always true. Which is given out that here when the ratio V by I, that is volt per ampere, that is potential difference per current, which is always defined as the resistance of the conducting material. So here this equation which was found by the George Simon Ohm, so on his name only we are to be calling and giving the units for the resistor is nothing but a ohm here. Okay. So here you can able to on x-axis voltage and y-axis ampere current. Okay, voltage which is will be measured in volts and the current which is measured in ampere. So that how exponentially when the voltage is going to be increases, exponentially the current which is going to be offering more and more here. Okay. So you can see here nearly zero point 0.8 at zero point 0.2 volts. Okay, 1.8 and that is a 0.2 na 0.18. Similarly at a zero point 0.4 volt is 0.45 like that here and zero point 0.6 it is 0.8. That means exponentially the current value which is going to be increases. Whereas in the other graph which is representing that here the current in a vacuum tube. Okay. So that is also your conductor, but the thing is that here is that vacuum tube is going to be obeys the Ohm's law or not. How you are going to be checking out means here if the voltage increases here, the current value, how the value which is going to be given out here. See here 100, 200, 300 volts, how 20 ampere of current, 40, 60, 80 like that here. It is stopping here. But the thing is that here there is no current at all. Okay, in this figure. So that it is not going to be always this. And here also zigzag, a curved type of uh, graph which is going to be representing here. This is about the thermistor, how the current which is going to be varies out with respect to the voltage. You can easily see that. Okay. So which may have the shape of the curve which is going to be attributing the large negative temperature coefficient. Okay. This is not positively increasing. Again, it is going to be reducing here. The resistivity of the material which is to be prepared by a thermistor. Okay. Next, temperature coefficient of resistor. Temperature coefficient. So here which is you can use this temperature coefficient in the lease experiment. Okay, the thermal conductivity of a bad conducting material. There itself, you want to calculate the temperature coefficient means here the chamber which is going to be heated up with respect to the time, how the temperature is gradually increasing later on if you are going to be cooling down, how the temperature is gradually decreasing. You can able to observe that which may gives you here a temperature coefficient of the material here. But the thing is here, the temperature coefficient of the resistor alpha, which is going to be denoting here. So by this, how we are going to be calculating different materials which may have the different resistivities as well as the temperature coefficients. So for a silver, this is the resistivity and this is the temperature coefficient. For copper is 1.7, this is the 3.9. Aluminum is 2.8, temperature coefficient is 3.9. Like that here. Okay. Resistivity from the atomic viewpoint and mean free path. This is not an important question. Uh, so the summary which may gives you here, a good conductor means which may offer more and more number of free charge carriers which can easily carried out by the charge carriers from one to another place. So that these carriers which are going to be how these are to be moving from one to another terminal means you need to apply such a external force. That external force which is coming out from the field here, capital E or V. So the current per unit area in this, which you can call it as a current density. Okay. And the charge density, which is always proportional to the uh, charge of the charge carriers, and how many number of charge carriers which are present inside the material, capital N, and also average drift velocity, VD. Okay. And here conductivity of the conductor which may depends upon the mobility of the charge carriers, and resistivity and conductivity of the intrinsic properties of the material. Intrinsic means pure. Okay. And also which is depends upon the temperature but not depends upon the size and shape of the conductor. Whereas the temperature at a given temperature, here the potential difference between the two ends of the conducting material, which is always proportional to the current I which is passing through it. Okay. So it is known as a Ohm's law, which is going to be obeys the Ohm's law. That is a ohmic material. If it doesn't obeys the Ohm's law, those are called it as a non-ohmic materials. Okay. So the vacuum tubes, gas tubes, semiconducting thermistor, thyristor, it does not obey the Ohm's law. These are the non-ohmic type. Okay. These are also called no ohmic, non-ohmic. Okay. NON. Next is the electrons are the carriers of the current. We know that moving charge carriers which may constitute the current which is going to be passing through any conductor here. Those are colliding with the with each other and colliding with the walls of the conductor. So there itself it may gains the more and more energy, but the thing is that here friction developed, temperature increases, and those are going to be gaining the energy, somewhat it is going to be losing the energy. Okay. So but here the energy which is appeared like a heat here, temperature rises, the rate of amount of heat which is developed in a linear conductor which is always directly proportional to the square of the current passing through it. Okay. I square. So the unit of the electrical power is watt. Okay. So we'll go for how the questions are going to be given out. Reduce the expression for the resistivity of the conductor. This is a very, very important. Give the Ohm's law. State and explain the Ohm's law. What are non-ohmic resistors? Like that. And distinguish between current and current density. I and J. Okay. Current per unit area. Charge per unit area or unit volume. That is the charge density. It may be charge density. We are referring this term in the gas line electrostatic. There itself you can able to observe that. Okay. These are the example problematic questions. Next is the Kirchhoff laws. Okay. Second unit in this. Mm, so you need to go for the what is the electromotive force, EMF value, and what is Kirchhoff laws. Kirchhoff laws is two types are there. One is the Kirchhoff current law, another one is the Kirchhoff voltage law, KCL as well as the KVL. Later on, Kirchhoff law to the single loop point and multi loop point. That's it. But here a little bit of knowledge is required to go for this Kirchhoff laws and to understand this. Here, why we need these Kirchhoff laws here? So these laws and applications which are to be dealing with the different electrical circuits. So electrical circuit which may have an electrical network which is a complex, okay, not in a simplest form here, which may have a transistor, resistor, uh, so power source is there, okay, capacitor is there, inductor is there. Somewhat zigzag, a more number of these components which are present in any network. So that which is always in a complex manner, not in a simplest manner. And it is going to be consisting a number of current loops as well as the meshes. Okay, and is also containing a several loops and number of sources of electromotive force. So, easiest way to analyze these circuits in 19th century, Gustav Kirchhoff, which he is a German physicist, he developed a simple manner so that in batteries and generators, there exists an ability to maintain a potential difference between 2 points which they are attached here. So these devices are called seats of electromotive force. And Kirchhoff first law. What is Kirchhoff first law? KCL. KCL is the Kirchhoff current law. This is a first law. Okay. The algebraical sum of the current meeting at a point is equals to 0. That is the Kirchhoff current law. Or else the current entering towards a junction which is also always equals to the current leaving from the same junction. That is the Kirchhoff current. And what about the second law here? Second law, which is nothing but the sum of the EMFs, the electromotive force, around any closed circuit, which is equals to the sum of the all the voltage drop across the impedance Z in that closed circuit. Z equals to V by I. Okay. Impedance formula Z equals to V by I, voltage per current, which is nothing but a impedance here. So that summation over capital E equals to IR, that is a KVL. So E is nothing but a V. E in place of V, we are writing EMF E. So electromotive force. Some devices here two circuits which are given out here. One is that you can go for it. What is that? You can discuss with this circuit diagram. So the first diagram which may have, you can easily observe that if this is a battery here, okay, a positive terminal and this is the negative terminal, the current which is passing through it. In series, a switch S is connected here, and in series, a resistor which is connected here. So that other end of the resistor which is connected to the negative terminal of the battery. The thing is that here how the current which is going to be flowing in this circuit when the EMF electromotive force which is to be generated by this source here and the current which is going to be passing through it, when the switch is going to be closed here, then the current which may come across the resistor here. If I and R is there, definitely there should be a V is there. Why? Because of Ohm's law, which is going to be stating here I current. I current which is going to be passing here, that this is the closed circuit. If you say I is there, R is there. So what is that? V equals to IR. In place of V, E are going to be writing it. So that you can easily estimate that what is the potential difference between the two terminals, plus and minus. You can easily calculate. The thing is happening only when the switch is going to be closed. If the switch closed, then the current is passing across the resistor. You can easily estimate this. Okay. But whereas in this case here, You can have the tap here, the water flowing here in this direction, so that through the pipe, this is the pipe here. Okay, pipe, zigzag pipe, which is going to be look like a resistor here, and a tap is there, open and close, which is going to be act like a switch here. This is the source. That means this is the source here. Okay, both are same, but the thing is that with respect to the uh, water, how the current which is going to be flowing in a circuit, you have been discussed. The same thing. Water pump valves are there. When it is high pressure and where is the low pressure? High pressure is at 0.3. High pressure current is coming. If it is in a zigzag manner, the pressure should be reduced here. Okay, this is not in a direct. So similarly here also, if it is in a zigzag, the pressure should be more current which is coming out. If you want to stop that current here, that should be like this, the symbolic representation. Okay. So in Indian others, those are going to be representing the resistor symbol should be like this. Whereas in foreign books, the resistor symbol should be like this. Okay. But both are same. No need to worry. But where is a higher potential, where is a lower potential, that is also you can. 6 and 7. So what is the energy which is going to be transferring within the stipulated time here? That is EMF E equals to dW by dq. Okay. Work done to carry the charge here. Or else dW equals to E into dq. Same equation. So power P equals to dW by dt. You know pretty well what is dW E dq. E dq by dt. What is dq by dt? Rate of change of charge is nothing but a current, na? So that power P equals to EI. That is the formula. That's it. Next, Kirchhoff laws. Most important. So in this Kirchhoff laws, a electrical circuit is a complex. Why? Because it may contain the sources, generators, resistor, capacitor, inductors, everything. That's what we can say that this is a complex circuit. So it may have a meshes, loops, all. So that and also number of EMFs and also number of sources are there. So that here by implementing the Ohm's law, which is very difficult in the case of this one. So what is the easiest way to find out analyzing these circuits? And so here Gustav Kirchhoff, he is a German scientist, and he developed two last year. So that one is KCL and another one is the KVL. So Kirchhoff current law, what it means here, which is stating that the sum of the current entering a junction which is equals to the leaving from the same junction. All or else you can denote this law, the algebraical sum of the current meeting at a point which is equals to 0. Okay. So summation over I entering which is equals to summation over I leaving. And KVL, Kirchhoff voltage law, what it states. It is stating that the sum of the EMFs around any closed loop of the current which is equals to the sum of all the voltage drops. Okay. Across the impedances in the closed circuit. So E equals to summation over IR. Okay. So illustration of the Kirchhoff's law and a single loop. So here, what is the E value in this circuit? here. What is the E value? You know pretty well, according to the KVL. E equals to IR, where small r is the internal resistance. Okay. And this is the small r and the current which is passing. And this is the IR. Okay. So E equals to small I into R plus capital I into R, or small I into capital R. So how you are going to be simplifying this? This one from this equation. E minus IR minus capital Ri equals to 0, or else here I by commoning R plus R, or else I equals to E by R plus R. So a single loop circuit 6.28, which is a rectangular block, which is a set of EMF E with an internal resistance small r. Okay, so many print mistakes are there. Please correct it. Which may gives you here a straight line. Uh, so the potential changes at the one comes across the traversing the circuit in a clockwise, and one which is a set of EMF, and this is an external resistor. Third point which may gives you potentials. So illustration of Kirchhoff laws to multiple loop circuit. How many loops are there? Here two loops are there. This is the one, this is the second loop. Okay. So the thing is that you can go for it by considering this one. This is EMF here given first loop, and other EMF is which is in second loop. So E1 into I1 into R1. Why? Because of here across the resistor R1, I1 current which is going to be passing out. So you may observe that here the E1 which is a generated potential difference, and here also which may comes in this loop here. So multi loops are there. The current should be here I1 plus I3. I1 plus I3 both are in downwards. I2 which is in opposite direction. So minus I2 equals to 0. Okay. So in this by loop theorem, I1 is E1 plus I3 R3 minus I1 R1 equals to 0. By simplifying this, you may get this equation. But only the thing is that you need to do practice. So like that, all the devices like generators, motor, battery, which may have the same capacity to maintain a potential difference between the 2 points, so that when they are going to be connected, these you can call it as a sources of the electromotive force. But in any electrical circuit, it may have a junction of the algebraical sum of currents which is at zero, and the algebraical sum of the charges in the potential encountered in a complete transverse traversal is zero. These are known as a Kirchhoff's laws. Okay. So what is Kirchhoff first law? Uh, the sum of the current entering a junction is equals to the sum of the current leaving the junction, or else any junction, the algebraical current must be equals to 0. Whereas the second law is the sum of the EMFs around any loop of current, which is equals to the sum of all voltage drop across the impedance in the closed circuit. So where we can apply these Kirchhoff laws? These you can apply in a multi-loop circuits. Okay? Not in a single loop circuits. You can easily apply it in a multi-loop. These are the questions. What is electromotive force in relationship? There is a problematic questions also there. Next, last one is the network theorem. Okay. So here mesh and node analysis, superposition theorem, and reciprocity, Thevenin's theorem, Norton's theorem. Okay. So why do we go for it? Let you discuss it. Well, starting onwards, we are discussing that if any electrical circuit is there, it may contains the impedances uh, or elements like resistor, inductor, capacitor, generators, EMF sources. If all these present, there you can call it as a electrical network. So that it means that electrical network is nothing but a combination of circuit elements. If linear and non-linear network, if you say, where network is said to be linear when the current in all branches is directly proportional to the driving voltage. Okay. If voltage increases, current is also going to be simultaneously increases. That network you can call it as a that you can call it as a network, a linear net. Okay. In case of voltage and current in any branch network is non-linear, then the network is said to be non-linear. Both voltage and current, any branch of the network is non-linear. Somewhat it may be increases, somewhat it is to be decreases. It's okay. That you can call it as a non-linear. But what is a network theorem? A network is a problem which can be often by solved by the application of Ohm's law and Kirchhoff's laws. But network is a complicated circuit. So many calculations you need to do it. by implementing the laws, which are very tedious and cannot be worked out on these laws. Therefore, more convenient methods can be chosen here. So some theorems provides easy solution to such problems, and complicated the network to be can be very easy. Okay. So these theorems we can call it as a network theorems, which we are going to deal with this reciprocity, Thevenin, Norton, all these. Next is the mesh and node analysis. Node analysis. In the process of the circuit analysis, some meters which are used to measure the current flow in a circuit, but the ammeter works effectively for supply of the low frequencies. Whereas for high frequency supplies, voltmeter works more effectively than the ammeter. For lower frequencies, ammeter. Whereas for higher frequencies, voltmeters. Okay. So that the voltage information at different node points will be taken. So I equals to V by Z, you can call it as a Vy, which is a admittance. Y is a admittance. So this is the battery E1 and an E2. How many resistors are there? You can go for it. Admittance Y1, Y2, Y3, Y4, Y5, Y6. Okay. All which is offering such a current. I1, I2, I3, I4, I5, I6. Getting? There are 6 resistors of admittance. Y1 to Y6 batteries. EMFs are 2 only, E1 and E2. The potential at O. What is the potential at O? This is considered to be 0. Then left part and right part at ABC, small ABC, EAEB. Therefore, what is the potential difference across Y1 is E1 minus EA, Y2 EA minus EB, Y3, Y4, Y5, Y6. After calculating, after simplifying, you may get this. So like that you need to, what is superposition theorem? I just explaining how to read out and how to do this. So in any circuit statement, if containing resistance and network, so that the current flowing through a point is equals to the sum total of the individual currents flowing in the each network. But while deciding the flow of current through a network, we may imagine that their internal resistance in plane of the other networks. If there are voltage networks and current networks working at a time, each network will work independently. That is why we can calculate the effect due to the individual network. So the current flowing through a resistor, which is equals to the sum of the total of current through the individual networks. Similarly, potential difference, which is developed across a resistance, is equals to the sum of total of potential difference developed due to networks. Okay. So this is about the superposition theorem. See here. Impedance Z1, current I1. Z2, I2 double S. This is E2. If it is E2, if it is E1, both are present. How we are going to simplify? Reciprocity, superposition theorem, which may gives you I1 equals to I1 dash plus I1 double dash. Similarly, I2 equals to I2 dash plus I2 double dash. In any network containing more than one voltage or current source, the current through any branch is uh, the sum of the currents due to each source, sum of the current due to each source acting independently. Reciprocity theorem. What is the statement here? If an EMF is applied to one mesh of a network of linear impedance, which produces a certain current in the second mesh, then the same EMF acting in the second mesh will be given an identical current in the first mesh. So E and I, which may be mutually exchanged, whereas V by I is known as a transfer resistance. Next, Thevenin theorem, most important theorem. The current in a load resistance which is connected between two terminals of a network of generators and linear resistance is same as due to single voltage generator EMF equal to open circuit. That means there is no load resistance. Voltage between the same terminals of the network and internal resistance is equals to the resistance of the network between the same terminals of the network when all generators in the network have been replaced by their internal resistance. That you can call it as a Thevenin theorem. ETH, RTH, R2 plus R1 by R1 plus R2. ETH value. Similarly, Norton theorem. This theorem is very useful in converting complicated network into a simple parallel circuit. What is the statement of the Norton's theorem? The current in a load's resistance between two terminals of a network of generator resistors, which is in the same as if the load resistance were connected to a constant current source. Whose the generated current is equal to the short circuit current between the same terminals of the network, which is placed is parallel with the resistance and equal to the resistance of the network looking back into the terminals when all the generators in the network have been replaced by resistance equal to their internal resistance. That is the Norton theorem. So IN value. See here, network of generators linear resistance. This is the two terminals A and B across the load resistance. This may be replaced as IN here, and before that RN is there. So across the load RL. Simplified form. And also this is the procedure how to take and how to do this. In the practical itself, this is the best procedure. How to calculate the Norton current and Thevenin current applications, IN value or RN value, R2 plus R1, R3. This is the duality. Summary means many complex networks in an electrical engineering and electronics, which can be analyzed by making use of the Thevenin and Norton theorem. With the help of these two single networks, it becomes easy to understand the working of each network. So each of the network discussed, which is individual importance. These theorems which are applicable for the both AC and DC, alternating current and direct current networks, which is also used in complex networks containing of vacuum tubes and also transistors. Problematic questions also given. Okay. So by coming class, we will go for the magnetostatics. There itself we can discuss Ampere's law, Biot-Savart's law, and this one. Okay, right. Thank you.